So this one is an assignment which is related to the nuclear decay and the binding energy. We discussed the first 9 questions from this assignment and question 10 onwards. A student investigated the absorption of a gamma radiation by iron. She placed a gamma source in a holder and set up a GM tube a short distance away. She placed a thin sheet of iron between the GM tube and the source as shown. The student used 5 different thicknesses, as you can see, to determine the count rate. As the thickness is increasing, the count rate will decrease as the absorption will occur. The count rate with no iron sheet is placed, that is R naught. After passing through an iron sheet, the thickness is X. The count rate R is given by this equation. R is equals to R naught e raised to power minus mu X, where mu is a constant. A student plotted her data. The student used her data to plot a graph. As you can see, ln R versus X. The student used a gradient of a graph to determine the value of the mu, and she used this to estimate the half value thickness of iron. This is the thickness of iron that used to reduce the count to half. Student used a source that emit a gamma radiations of energy 1.1 mega electron volt. Deduce whether the data of the student obtained confirm this energy value. And half value thickness is about 1.1 and gamma rays in iron is 1.5 centimeter. So first, we have this graph, as you can see, and the equation is there. So we'll compare, because we are plotting a graph between ln R and X. So we have to modify this equation first. So if the equation is R equals R naught e raised to power minus mu X. If we take, because the graph is between ln R and X, so we have to separate them. If we take ln both sides, so it will be ln R equals to ln R naught plus, because when in logarithm two quantities are multiplied, they will we write them in addition, ln e raised to power minus mu X. And ln and e anti-function, so we can say ln R equals to ln R naught minus mu X, because ln and e cancel out. Then if we rearrange the equation, ln R is equals to minus mu X plus ln R naught. Now we'll compare with the equation of straight line, which is y is equals to mx plus c. So on y-axis, if you make ln R, that we are making on y-axis ln R. On x-axis, if we have x, on x-axis, if we have x, what will be the gradient for us? The gradient will be equal to minus mu. So using the graph, first we'll find the gradient, and our gradient will be equals to the minus mu. So using a gradient, a negative gradient will give us minus mu, and then the half-life, like the half thickness, because the second part, first we have to find the gradient to get the value for minus mu, and the second part, as a student, use a gradient to determine mu, and then use this to estimate the half value thickness. And this is the thickness of iron that would reduce the count to R naught by 2. Like half value thickness is reduce the count to R naught by 2. And the student use a source that is emitting energy about 1.5, deduce whether the data of student obtained confirm this energy. And half value thickness for 1.1 is of iron is about 1.5. So we have to just show that the half value thickness is 1.5. So as we derive this equation that the gradient will be equal to minus u, so we can take any 2 points. The first point on x-axis will be x1. The first point on y-axis will be y1. So this will be equals to x1 and this one is equals to y1. And we take another point that is x2 and y2 and we get a negative gradient. Because the y1 is above y2, so the value of the gradient will be negative. This is x2 and this is y2. So value of the y, each box is like 0.05 because 10 boxes equals to 0.5, each box is 0.05. So this will be 5.55, then 5.6, or because this is from 5, this will be 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, and 5.7 of 5.65. This is 5.65. This one is 6.6. X1 is 0.5 and X2 is 2.5. So we use a formula for the gradient, which is y2 minus y1 over x2 minus x1. So gradient is equals to y2 minus y1. Y2 is for us 6.6 minus y1 is 5.65 divided by x2, which is 2.5 minus x1, which is 0.5. So what's the answer for the gradient? 6.6 minus 5.65. So this will be the final answer. 0.457475. So when we work out the gradient, the final, and it will be negative because this is because when we substitute it's y2 minus y1, so it will be negative like 5.65 minus 6.6, so this will be minus 0.475. That is our gradient, and we know our gradient is equals to minus u. So when we substitute minus 0.4 minus 0.475 is equals to minus u. So minus will cancel with minus. So mu is equals to 0.475. So 0.475, we got the value for mu. Now, after getting the value for mu, we have to show that when when the radiation we receive is R naught, the value of the x, because we got the value for mu now. So when the radiation will become half, the R will be equals to R naught. Like this will be R naught by 2. This will be R naught e raised to power minus mu x. X is the value, like the half thickness value when the radiation become half. So R naught will cancel. In place of R, why we substitute R naught by 2? Because the radiation become half of its original value. That's why we substitute R naught by 2. So this will be 1 over 2 is equals to e raised to power minus mu x. If we take ln both sides, so when we are taking ln both sides, this will be ln 1 by 2 is equals to ln e raised to power minus mu x. Ln and e will cancel, and ln half is equals to like minus 6.93, 0.693, and ln and e will cancel that minus mu x. Negative will cancel the negative, 0.693 divided by mu is equals to x. And value of the mu, we already worked out that it was 0.475. So 0.693 divided by 0.475, that will give us the value for x. How much is x when we divide this? 0.693 divided by 0.475. What's the value for this? 0.693 divided by 0.475. 1.46. So 1.46 centimeter, or we can, so that is what we have to show, that the thickness is about 1.5 centimeters. So 1.46 is about 1.5 centimeter. The next question, iodine 131 is a radioactive isotope used in range of medical procedure. The activity of a sample of iodine 131 is 1860 megabecquerel. Calculate the number of the atoms of iodine 131 in the sample. Half-life is 8.02 into 8.02 days. So we have the original activity is there, and half-life is also given. After half-life, the original activity, and we have to calculate the number of the atoms of iodine in the sample. So first what we'll do, we have the half-life, so we'll work out the lambda first, because lambda is equals to 0.693 over T half is equals to 0.693 over lambda. So using the half-life, we'll work out the lambda. And then using the activity, because the activity means how many activity is equals to ln. N is equal, basically, this formula, how many atoms have changed, activity is equals to n lambda. So if we want to find number of the nucleus present, so it will be activity multiplied by lambda, that's equal to n. As n is equals to a lambda, we can work out by this. So first we have to work out the lambda. So we have the formula that T half, the half-life is equals to 0.693 divided by lambda. So lambda is equals to 0.693 divided by T half, but that is given in days. Activity, how many disintegrate per second? That is becquerel. So we have to convert time into second. So this was 0.693 divided by the time which is given in days. That is 8.02 days. We have to multiply by 60 to convert into minute, and then multiply by 60 to convert into second. So this will give us the value for lambda. And this formula, activity is equals to n lambda, not so activity, because activity is n lambda. So if we need n, it will be activity divided by lambda. So after working out the value for lambda, which is 1 exponent minus 6. So when we work out the value for lambda using this formula, that lambda is equals to 0.693 divided by T half, and 0.693 divided by 8.02, this is 60 into 60. This will give us a value for lambda, which is 1 into 10 to the power minus 6 second inverse. And then we have the formula activity is equals to n lambda, like number activity is proportional to number of the nucleus present. And when we replace the proportionality sign, we replace with equal to and constant. So lambda is a decay constant. So we have the activity. So if we need n, activity divided by lambda is equals to n. What about activity? Activity is 1860 megabecquerel. That's like how many disintegrate? This many disintegrate every second. So it should mean becquerel, so 1860 into 10 to the power 6, because mega is there, and divided by the lambda, which is 1 into 10 to the power minus 6. So when we substitute, we'll get 1.86 into 10 to the power 15. That is the number of the nucleus which are present in this time. Is it clear, this one? Then question 12. A student determined the count rate of a radioactive source. She used in an americium source, which is an alpha emitter. The student connected a detector to a counter. Explain why the detector should be positioned a small fixed distance from the source. Because alpha source have very small range. Alpha particles cannot travel long distance. That's why the detector must be placed at a closer range. As the count rate depends on the distance between the source and the detector. Student measured the count for 2 minutes and divided this by 120 to determine the count rate. And explain two modification to the student method that will improve her value for the count rate from the source. So as you can see, student did not calculate the background radiation. So first, student should calculate the background radiation, and then because random nature, because radioactivity is a random, so uncertainties are there. So she should take measurement for a longer time and repeat the measurement. Like she must calculate the background radiation. That is one thing. And measure the radiation for longer time. It's like 2 minutes is a very short time. So two modifications, that's a 4 marks. So one is when you mention like background radiations should be measured and then should be subtracted from the original to get the count from the source. And second thing, because radioactivity, it's random, so it will induce the uncertainty. So she should measure for a longer period of a time. The next, in an experiment, nuclear fusion reactor, a magnetic fields are used to confine a hot plasma. This is to sustain a controlled nuclear fusion. Explain why it is difficult to sustain a controlled fusion reaction. A very common question about like a why fusion cannot be maintained for a very long time. What is the reason for that? Basically, extremely high temperature plasma, like first we need a very high temperature plasma to give enough energy to overcome the electrostatic repulsion. And we also need a very high density plasma so that more collision will happen. And what normally happen if the plasma or the nucleus or the particle touch the container, they lose the energy, so the temperature decreases. So for that, we need a very strong magnetic field. So why it is difficult to sustain a controlled nuclear fusion reaction? First, for nuclear fusion reaction, we need very high temperature. To collide or to overcome the electrostatic repulsion, very high temperature is required to overcome the electrostatic repulsion. And second thing, we need very high density to collide or increase the rate of collision. Then what happens when plasma contact with the container? It lose energy. So we need strong magnetic field to reduce the chance of contact between the plasma and container. That's why like it's very difficult to have a sustained controlled fusion. Like these conditions are very difficult to maintain. The next question, the graph shows how the mass per nucleon varies for a range of nuclei. Explain using a graph how fusion process is able to release the energy. So mass per nuclei here, iron is having the least mass per nuclei or more binding energy. So how this one releases energy. So basically nuclear fusion, what happened, the lighter changes to the heavy. Like we have initially from the graph, you can see the lighter have more mass per nuclei and the heavy nucleons, heavy atoms have less mass per nucleon. So it means the mass will decrease. Originally, the mass will be more and later the mass will be less. So what will happen to this mass which changes per nuclei? This converted into energy. That's why the nuclear fusion reaction release energy. So in the fusion process, the low mass nuclei, the mass per nucleon decreases. And as the mass decreases, that correspond to release in energy, and we can use E equals mc square to work out this. Explain using a graph the limitation to the element suitable for fusion. Like here, the heavy nucleus, like iron is the lowest point, but iron, which is having the smallest mass per nucleon, so fusion nuclei more massive than iron will require energy input. Like we need lot of energy. Instead of here, what will happen when it is converting from hydrogen to helium? The reaction will be exothermic. It will release energy as the mass is decreasing. That extra mass will convert into energy. But from iron to the heavy, like example till uranium, what will happen? It will become an endothermic. Why? Because to produce them, the mass per nucleon should increase. So from where we get that extra mass, we have to supply energy, or the energy must be input. So the fusion reaction is only possible for the lighter nuclei, not for heavy nucleus. In question 14, the low activity sealed radioactive source are used in school to demonstrate the properties of ionizing radiation. The source and the radiation that are emitted, americium is there, radium is there, strontium. Said what is meant by activity of a radioactive source. Activity of radioactive source means how many radiations it emit out every second, or rate of a decay of unstable nuclei. Better learn the definition. Rate of decay of unstable nuclei. Describe an experiment using the absorber of different material that could be carried out to identify the source. You must explain how the data collected should be used to distinguish between the sources. So one is alpha source, another one is alpha, beta, and gamma source, another one is beta, gamma source. So first what we will do, like first, whenever the question is there, for these, we always record the background radiation. So we always record the background radiation. That is the first thing. Then we'll fix one source closer to the GM tube. The source should be close. Then after that, we will, if a paper, if you, like example, we place a paper, the count will reduce to background. It means, or even aluminium also. So if paper is placed and the count rate reduced to the background, I'm writing BG, it means that it is americium. Then if the paper does not cause any change, because the three sources, what we have either americium is alpha, then strontium is beta and gamma, and radium is alpha, beta, and gamma. So very small changes there, because radium is giving out all three, alpha, beta, and gamma. And if very small change is there, or if there is no change with paper, it is strontium, because strontium is beta and gamma emitter. And if aluminum is added between the source and the detector, it is radium. Because as you can see, the three sources, one is only alpha emitter, radium is alpha, beta, and gamma. So when we place aluminum, it will be like only gamma will be there, and gamma does not cause too much ionization. So the count rate will be very low with gamma. Then the school has a gamma source with a stated activity of 185. Don't forget to convert like kilo or a megabecquerel to becquerel. So it will be 185 exponent 3. The current activity is 20. If both like are there in kilo, so we don't have to convert unit, as that will cancel out, but it's fine. So 25.7 into 10 power 3 becquerel. The calculate the time elapsed since the source was produced. So the school has a gamma source with a stated activity. Like this was stated activity, but the current activity we have the half-life. So first, using the half-life, we'll determine the lambda. So lambda is equals to 0.693 divided by T half, because T half is 0.693 lambda. So first we determine the lambda. If the unit of the time, like example here, we can convert into seconds. It's fine. If you don't convert into second, that's also okay, fine. It doesn't, because the final answer will be in years when you solve. If you convert the time into second, then the final answer will be in seconds. First, using this, we work out the lambda. So 0.693 divided by T half, which is 5.26 years, 0.132 years. And then using the formula A is equals to A naught e raised to power minus. So we have the formula A equals A naught e raised to power minus lambda T. A naught is an activity after a certain time interval. So that is 25.7 kilobecquerel, so 10 power 3. A naught is the original activity, which was 185 becquerel, kilobecquerel. So 185 into 10 power 3. E raised to power minus lambda. So lambda we already worked out, that is equals to 0.132 years. And T we want to determine actually T. So this is multiplied, this will go there in division. So it will be 25.7 into 10 power 3 divided by 1.185 into 10 power 3 equals to e raised to minus 0.132 T half. After getting this, we'll take log both sides, because to cancel out ln both sides and simplify. So it will give us the total time of about 15 years. It will be 15 years. So the activity changes from 185 to 25.7. In question 15, in a nuclear power station, a nuclear reaction that release energy which is used to produce steam which drive the turbine and generate electricity. In 1939, Lise Meitner discovered that the uranium isotope of 235 undergo a fission when it struck with a slow neutron. A nuclei of a barium and a krypton are emitted. The reaction releases a 200 mega electron volt. Most of this appear as the kinetic energy of the product. Complete a nuclear equation which represent this. So we just have to, uranium is there. So total at the denominator should be 92. So 36 are there. 92 minus 36. So we will have 56 here. And there are three, because total 235. 141 plus 3. Here total 3 multiplied by 3. So 144 minus 235 minus 144. 236. Now because 235 plus what? 236 total here. This is 236. This is 141. 3. It will be 92. Why the energy is released in this reaction? So what will happen? The mass of the product, always the same concept. Like the product mass will be less than the reactant mass. So that mass has converted into energy. And we can use the formula E equals mc square. Explain why the fragment must move away from each other. Because if the original initial momentum is zero, the final momentum should also, like, to conserve the momentum, because uranium is there, so initial momentum of uranium is zero. So what should be the final momentum? The final momentum should also be zero. That's why the fragments which are produced must move in opposite direction. If a barium is moving towards right, the krypton will move toward left. And the heavy fraction will move slower and the lighter fraction will move faster. The diagram represents a nuclear fusion reaction. Write equation for this. So the isotopes of a hydrogen 2 1 plus hydrogen 3 1 combine to give helium as a product and one of the neutron. Calculate the energy released in joules when this fusion occurs. So how to work out the energy release? So first what we do, we work out the total mass of the reactant. Then we work out the total mass of a product, total mass of reactant M1, total mass of a product M2. And we take a difference of the mass to know how much mass defect. And after getting the mass defect, we'll use a formula E is equals to mc square to know how much energy is released. So these masses are already given in mega electron volt per c square. Mega electron volt per c square is a unit of mass. So when you take the difference, like take these masses in mega electron volt per c square and take the difference to get answer in mega electron volt per c square. And that will be same as the energy released in mega electron volt. So we'll at the last convert this mega electron volt into joules. Like first we have the reactants. These are the reactants. So 1875.1 plus 2807.9. That's a reactant. Minus the product, that is a helium, plus, so this is 3726.4, and plus the mass of a neutron 939.6. When we simplify this, they take sum and then take a difference. It will be a 17 mega electron volt per c square, which is a unit of mass. And the mass of mega electron volt per c square means when this mass will change into energy, it will release 17 mega electron volt. Now we have to just convert this 17 mega electron volt into joules. So first 17 mega electron volt we convert into electron volt. So 10 power 6, that will be electron volt. Then to electron volt into joule, we multiply, because 1 electron volt equals to 1.6 into 10 power minus 90 joule. So we just multiply this. So 17 mega electron, 17 into 10 power 6 electron volt times 1.6 into 10 power minus 19. So when we multiply, this will be 2.72 into 10 power minus 12 joule. So that is the amount of energy released in joules. So whenever a question is there, even it's a nuclear fission or a fusion, always the same case, you first find out the mass of reactant, then the mass of a product and take a difference. Explain why extremely high temperature are required. That we, like the previously this question was having 4 marks in which we have to mention why for a sustainable fusion, why it is difficult. Here, why extremely high temperature is required for, especially for nuclear fusion. So we have to overcome, like the particles must have very high kinetic energy, so they overcome electrostatic repulsion and fuse together. So we have to overcome the electrostatic repulsion between the nuclei. The particles or the nuclei must have high kinetic energy. That's why we need a very high temperature and fuse them. Two advantages of obtaining a nuclear power from on Earth from fusion rather than fission. Look, fusion, the fission, mainly the fission reactants are radioactive. So, but fusion does not produce radioactive. And second thing, like amount of hydrogen will have infinite fuel for a fusion rather than fission. So the two advantages does not produce a new radioactive waste, and we have infinite, you can say like too much. So it does not produce the radioactive waste. That is one thing. And the second thing, like the fuel, we have infinite fuel available. But for fission, we have like limited amount of uranium is there to undergo a nuclear fission reaction. So this was the exercise related to nuclear decays and binding. The next session, I will do more questions and we will do another topic. The last we did simple harmonic motion. So after simple harmonic motion, it's like the last topic is about astrophysics and cosmology. That will start next week.